let me start with the prime implicant. Remember that in the case of Carnot map, we try to combine adjacent squares, but would like to combine the maximum number of adjacent squares. So the meaning of prime implicant, it's a product term obtained by combining the maximum number of adjacent squares. That's the meaning of prime implicant. So always we combine the number of combined squares must be power of 2. Yeah, for example, we can combine 2, we can combine 4, we can combine 8, and so on. So it's always power of 2. The meaning of essential prime implicant, so it becomes essential if you cover at least one midterm which is not covered by the other prime implicants. So here you can mark the midterm which is covered by the prime implicant, which is not covered by the other prime implicants, which makes it essential. So that's the meaning of essential prime implicant. So you can distinguish between a prime implicant and an essential prime implicant. I'm going to give you an example to make this very clear. Right. So here's an example. It's a function of 4 variables, A, B, C, D. And we have all of these are the prime, all of these are the midterms, which are listed in the sigma notation. So the question is to find all the prime implicants and all the essential prime implicants. This is the question. Right. So what we need to do is we need to draw the Carnot map. So this is the Carnot map of the function f. And notice that how we fill the Carnot map with the midterms. So remember the squares, okay? So this must be here midterm 0. This must be 3. This must be 2. Then this must be 5. This is 7. 8 is down here, 8. This is 9. This is 10. This is 11. And then we have 13 and 15. Okay, so you should remember the locations of these squares in the Carnot map. This is very important. Fine. So once we have filled the Carnot map, okay, with the ones of the function, you don't really have to show the zeros. Yeah, it's enough to show the ones because the other empty squares must be the zeros. Okay. So what we need to do is we need to locate the prime implicants and the essential prime implicants. Right. Can you see the prime implicants? Are they clear to you? Can you see what are these prime implicants?
Yes.
Okay. Can you tell me which ones? You can actually tell me which squares by their numbers.
One.
One is not.
Which one?
One is not even in the midterms.
So which ones are the prime implicants?
3, 7, 15, 11.
Okay, so this is actually 3, 7, 15, 11. Yes. What else can you see?
5, 13, 9.
5.
13, 9.
5, 13, 9. This is not.
Oh
the
no,
prime
we can't.
implicant.
We can't. Yeah, it needs to be multiples of 2.
5, 7, 13, 15.
0, 2, 3.
Say it again.
0, 2, 8, and 10.
0, 2, 8, and 10. Yes, thank you. Yes, this is also a prime implicant. Yes. What else?
5, 7, 13, 15.
Yes. 5, 7, 13, 15. What else?
9, 8, or 8, 9, 11, 10.
Yes. 8, 9, 11, 10. Excellent. What else can you see? Do we have more?
5, 7, 13, 15, 9, 11.
This is, I mean, how can you have a prime implicant that has 6 midterms? Can you have 6 midterms? Can you combine 6 midterms? Can a prime implicant, yes or no? Can you have a prime implicant with 6 midterms?
No, you have 2, 4, 8, and 16.
Exactly. So forget about 6, combining 6. Okay, can you tell me what is actually, can you find another prime implicant?
2, 3, 10, 11.
Yes, thank you. 2, 3, 10, 11. Excellent. So you can see we have located many of these. In fact, what you have to do is that you have to locate all of them. So I think that you have located all of them. So let us take a look. So we have this prime implicant, which is 5, 7, 13, 15. Now we can write the term for this one. Okay, so the term for this one is B and D, right? So this is B and D. We can look at those which are on the corners. Somebody mentioned them, the 0, 2, 8, and 10. Can you tell me what's the term? This is what? What is this prime implicant? Can you tell me the term algebraically?
B and
Is it B or is it
yeah,
B prime?
it's B prime and A, I think.
D prime.
It's A,
D
B
prime.
prime, and
D prime.
D prime. Thank you very much. D equal to 0. So B prime, D prime. Okay, so you have to be able to write the terms properly, okay, from the prime implicants. Otherwise, you will miss the question. طيب. We have these four. Somebody mentioned 8, 9, 11, and 10. So can you tell me what's the term?
A B prime.
Yes, AB prime. Somebody mentioned these four. Did anyone mention these four? 13, 15, 9, and 11? I don't remember. Can you tell me what's the term for these four?
D, B.
Okay, so
A,
it's what?
A D
It's A and
D, I think.
yes. And
What?
somebody mentioned these four, 3, 7, 15, and 11. What's the term? What is this one?
C D.
Yes. You can read it directly from the Carnot map. C is equal to 1, D equal to 1. So that must be CD. And we still have one more, which is this one. 3, 2, 11, 10. Somebody mentioned this before, as I remember. So can you tell me what's the term for this one?
BC.
How can it be B? B equal to 0.
B prime and C.
Yes, B prime and C. So you see that you have to write them properly and you have to practice doing it. So it's very easy, very simple. It's not really that difficult at all to obtain the prime implicants. So we have in total, we have 6 prime implicants. 6 prime implicants in total. So you have to locate all of them. It does not really mean that the solution has to contain all of them. Okay, what's important is to identify what are the prime implicants, all the prime implicants from the Carnot map. Okay. Now, can you tell me which ones are essential prime implicants? So we have 6 prime, but which ones are essential? Which ones are essential and why is it essential? And what makes it essential? What does it mean to have a prime implicant to be essential?
Covers terms that
it has to cover at least one minterm, which is not covered by any other prime implicant. So can you tell me which ones are essential?
BD and B prime, D prime.
Exactly. BD and B prime, D prime. So we only have 2 essential prime implicants. Only 2 essential prime implicants. Now notice that I'm putting a dot, and the dot here is to indicate that, for example, what makes B prime, D prime essential is that we have minterm 0 is covered by this prime implicant, which is not covered by any other prime implicant. The same thing for BD, it covers minterm 5, and minterm 5 is only covered by BD, and it's not covered by any other prime implicant. So this is why it is essential. Okay, is this clear? So we have solved this problem. We have identified all the 6 prime implicants, and we have identified that 2 of these prime implicants are essential, BD and B prime, D prime. Now, any solution, okay, any minimal sum of product expression for this function f should contain the 2 essential prime implicants. But it does not really have to contain all the 6 prime implicants, but it has to contain the essential, the two essential prime implicants. So any essential prime implicant should be part of the solution, okay, of the minimal sum of products. So let us look at the simplification procedure. I'll come back to the same example and try to obtain the solution, okay, for this function. So step number one is to find all the essential prime implicants. So what is important for me in order to simplify a function and obtain the minimal sum of product is to identify what are the essential prime implicants. And this can be easily discovered from the Carnot map. You can actually easily inspect the Carnot map, and you can discover these essential prime implicants. So it has to be prime. So it has to cover the maximum number of ones. It has to be power of 2, of course, the block size in the Carnot map, and it has to be essential. So therefore, you have to mark the minterm that makes the prime implicant essential. Now, this is step number one. So find all the essential prime implicants. Step number two, now check if all the essential prime implicants cover all the ones of the function. You are done. Yani sometimes you have a unique solution and therefore all the prime implicants are essential and you are done with step number one. But sometimes you might find that the essential prime implicants does not cover all the ones of the function. So what is important is that in your solution, to get the minimal sum of product expression, you have to cover all the ones of the function. So therefore, if the essential prime implicants does not cover all of them, all the minterms, so you have to add additional prime implicants to cover the ones of the function. Okay, so here we choose a minimal subset. You don't choose all of them. A minimal subset of the prime implicants that cover all the remaining ones, all the remaining minterms. And we make sure to cover all the ones which are not covered by the essential prime implicants, because the essential prime implicants are going to cover, okay, some of these minterms. So there is no need actually to use a prime implicant that covers ones that are already covered. So look at the prime implicants that cover the remaining ones. And we try to minimize the overlap, because there will be overlap among the additional prime implicants. So the idea here is that we want to have a minimal subset, okay? So once we have found the minimal subset, then we are done. We have the solution. Now, sometimes you will discover that a function can have multiple solutions. Yani there is no unique minimal sum of product expression, okay, for the function. And therefore, you can obtain multiple simplified expressions. Sometimes the function might have two solutions. It might have two simplified expressions. It might have three. It might have four, or even more. So all of this is possible. So you may be asked to list all the simplified sum of product expressions. Okay, so in the question, sometimes I ask the students, okay, please tell me what are all the solutions, all the simplified sum of product expressions for the function. So this is the procedure. This is what we call the simplification procedure using the Carnot map. Let us go back to the same example. This is exactly the same function that we have seen in the previous slide. Already we have identified that we have 6 prime implicants, but only 2 are essential. So I'm going to identify the essential prime implicants. So these are the 2, B prime, D prime, and BD. So this is step number 1. Look at the essential prime implicants, okay? And put a dot on the minterm that makes it essential, okay? So notice in B prime, D prime, it is minterm 0 that makes it essential. In BD, it's minterm 5, which makes this prime implicant essential. So these are the only 2 essential prime implicants. Next, we still have some minterms which are not really covered. So therefore, we are going to add extra prime implicants to cover all the remaining 3 ones. We still have 3 minterms. You can see we have minterm 3, we have minterm 9, we have minterm 11. These have not been covered yet. So therefore, what I need to do is that I need to add two extra prime implicants that will cover them. Now I have here more than one choice, okay, to cover the remaining ones. So we have multiple solutions in this example. So we can actually use these two. We can use CD and AD. This will be one solution. Notice that BD or B prime, D prime, they have to be part of every possible solution. So one solution is to add CD, AD. These are not essential. These are prime, but not essential prime. Okay. So we can actually add these two, or we can add these two, or we can add these two, or we can add these two. So therefore, we get four possible solutions depending on the selection of the remaining two prime implicants. And all of them have 8 minterms. Sorry, they have 8, literals. So all of these four possible solutions, they have the same cost, 8 literals, and all of them are minimal. So we have 4 solutions to this function, 4 minimal sum of product expressions. Questions? Is this clear? Students?
Why can't we add only 2 minterms? Why always a square?
Why we don't actually add only these 2? Right? And add only this one.
Yes.
You tell me.
No, not only this one, but the one.
Okay, these two.
Yes.
Okay, you tell me. Or anyone would like to answer? Yes, Muhammad.
If we add one only, you'll get 4 literals in it.
Yes, if we add one midterm, the midterm will have 4 literals. Yes.
Yeah, and if you add 2, you will have 3.
Exactly.
So
if you
really
combine
inefficient.
2 squares, you will get 3 literals. By combining 4, you can simplify it to only 2 literals. Remember that we would like to have a minimal sum of product expression. So if you combine only 2, okay, so if you look, you tell me what is the expression for these 2? Give me the expression for these 2, Ali. Give me the expression. I would like to combine these 2 midterms.
Yeah,
this one and this one. You tell me what's the expression for these 2?
A, B prime, D.
A, B prime, D. Now, what is better, A, B prime, D or AD?
AD.
AD. Now, you tell me if I take AD or AB prime D, what do you get?
AD.
Notice that we have here AD, here we have AD, right?
Yes.
So we have absorption, we have AD. Based on absorption, you can simplify it to AD. So why do I need AB prime D if I can get AD? You understand this point, Ali?
Yes, yes, it is clear.
All right. Right. Let us move on. Anyone has a question about this? So you can see absorption, you can see it directly from the Carnot map. So when you look here at not a prime implicant, for example, when you look at AB prime D by combining 2 adjacent squares, this is not a prime because you are not really combining the maximum number of adjacent squares. You get a term which is AB prime D, but it is part of AD, and therefore you can simplify it. That's really the idea of using prime implicants, combining the maximum number of adjacent squares. Right. So don't make this mistake, okay, in a quiz or exam. Look for the prime implicants, look for the essential prime implicants. You know that the essential prime implicants, they have to be part of any solution. Sometimes you can get multiple solutions. This is good. Like we had here 4 possible solutions. So you have to include BD and B prime, D prime in every possible solution. The choice of the remaining, okay, 2 prime implicants, you can choose them differently because they are not essential. You have multiple possible solutions. طيب. So what we have seen is sum of products. The question is, can I get the product of sums? Can I use the Carnot map to obtain the product of sums expression? Can I use it to obtain a different expression?
Yes, you can.
How?
Take zeros rather than ones.
Combine
Yes,
the
we
zero.
focus on the zeros rather than the ones. Yes, yes. But let us see how it is done. Okay, let us see how it is done. So here I have an example of a function. I'm going to draw the Carnot map. It's a different function. It's not the same as the one that we have seen before. So these are the minterms. Notice that the ones which are blank are the zeros. I'm not really writing zeros just for simplicity. I'm just leaving them as a blank, but we know that these are zeros. Right. If I would like to look here at my essential prime implicants, this is essential, this is essential, this is essential, this is essential. Now you can see this is essential because of this minterm here. The green is essential because of this minterm here. This is the pink one is essential and the blue one is essential. So therefore we have a unique solution. So we have 4 essential prime implicants and they cover all the ones. So I have to have them in the solution and my solution is unique and it has 8 literals. Okay, so these are the 4 prime implicants and these are the 4 essential prime implicants. So each one of them is essential and it has to be part of the solution. There is overlap between them, that's fine, as long as the prime implicant covers a minterm which is not covered by any other prime implicant. It's enough to cover one minterm, not covered by the others, then it becomes essential. So the point would like to cover all the ones of the function. Now, this is a sum of product expression. This is not product of sums. It is sum of products. How can we have it as a product of sums?
By using the zeros instead of the ones.
How?
Same thing.
Yes, you are right. You are right, Abdul
Or
Malik. Yes.
we multiply 4 squares. Or
Let me, okay. Maybe this is something new. So let me explain this point. Okay, so we're going to focus on the zeros, like you said, Abdul Malik. So what I will do is, okay, so in this example, all the prime implicants are essential, and this is my minimal sum of products, and it's a unique minimal sum of product expression. So there is no other solution. Now, we are going to look at the K-map of F prime. So let us take the complement of F. So the zeros become the ones, and the ones become the zeros, right? So the trick is that look at the Carnot map of F prime. So now you can see that I'm looking here. Let me obtain a sum of product expression for F prime. Can you see what are my prime implicants? Well, we only have 2, which are also essential, right? I can easily write an expression here. So these are my essential prime implicants for F prime. But this is not F. This is not the function F. This is F prime. This is the complement of F. So I'm going to write a sum of product expression for F prime. So we get C prime D prime or A prime B. Now, this is not F. This is F prime. And this is not a product of sums. This is a sum of products. So what I need a product of sums, not for F prime, for F. So what shall I do?
We
Take
get the
prime for
complement
both sides.
of the prime.
Yes, take the complement. Use De Morgan's theorem. So the nice thing about De Morgan's theorem, it will convert the sum of product into a product of sums. So take the complement of F prime. So F prime prime is equal to F. And then take the complement of C prime D prime or A prime D. We get CD, and so we get C or D and A or D prime. So notice that now my expression here is a product of sums for the function F. So we got, using the same Carnot map, okay, we got a different expression, but this expression is not a sum of product, it's a product of sum expression for the same function F. So now we have two expressions, one minimal sum of products that has 8 literals, and we have another expression here, which is a product of sums that has only 4 literals for the same function f, So we have obtained two minimal expressions, one minimal sum of products that has 8, it cannot really have less than 8, and we have obtained a product of sums which has only 4 literals. So which one do you choose? 4 literals versus 8.
Choose the 4.
Exactly.
Max.
We can actually use the 4. We can use the product of sum. So you see that from the same Carnot map, we can have not only sum of product, but we can have product of sums. So we can do both simplifications, and then we can decide which one is more minimal and which one we would like to choose. So both of them are minimal, but one of them has it's the sum of product. This is the standard form. This is the sum of product standard form, and the other one was the product of sums, which is also a standard form. Okay. So minimal product of sums will have only 4 literals, as we have seen in this example. Right. So now the simplification procedure. So what we have seen, let me conclude. So we need to draw the Carnot map for the function f and obtain a minimal sum of product expression for the function f. Now we draw the Carnot map for f prime, because if you just draw the Carnot map for the function f and you obtain, you will get sum of product expression. So now what we need to do is that we need to replace the zeros with the ones and the ones with zeros. So this is why we draw the Carnot map for f prime and replace zeros with ones, ones with zeros, and obtain a sum of product expression, but for f prime. And then we use De Morgan's theorem to obtain f, which is the complement of f prime. And then when you use De Morgan's theorem to take the complement of the sum of product, it becomes a minimal product of sums expression for the function f. So this is the trick, okay? So we take the De Morgan's theorem to take the complement of the sum of product for f prime, and this will give me a product of sums for the function f, okay? And then we can count the number of literals, okay? So which one is better, minimal sum of product or minimal product of sums? It depends on the function. And sometimes you will find sum of product is better. Sometimes product of sums might have less number of literals. So you have a choice to decide between the two. Okay, then you can actually decide that which one is more minimal. Any question about this? Is this clear? طيب.
Yes.
I need to talk about don't cares. Okay, this is also an important topic. Now, sometimes you might have a function table that may contain entries for which the input values of the variables will never occur. Or you might have output. The output value of the function is never used. So this actually can happen in some functions. So in this case, we say that the output of the function is not defined. So there is no value for it. It's not 0, it's not 1, it's not defined. So you have the choice to define it any way that you want. So we say that the output of the function is a don't care. And we write x value inside the truth table. And this x value, you can choose it to be either 0 or 1. So you have the flexibility to choose the value of the don't care to be 0 or 1. Now, this decision, whether to choose it to be 0 or 1, does not really matter. What's important is that we can choose its value to minimize the implementation of the function. So when I would like to minimize the function, and the function has don't cares, this will give me more flexibility to choose the value of the don't care to be either 0 or 1 to obtain a minimal expression for the function. I'm going to give you an example of a function with don't cares. Now, sometimes you might actually have a function which is defined over BCD inputs. So my input here is not in binary, it is a binary coded decimal. So it's BCD. And we know that input in BCD can go from 0 to 9. We don't really have we use 4 bits in BCD, and the input is only from 0 to 9. These are the only BCD possible values, but 10 to 15 do not exist. They are not really BCD inputs. So therefore, the input BCD can never be 10 to 15. So this input will never occur, and therefore, the output is not defined, okay, when the input is from 10 to 15. Now, the function here is defined such that if the input is from 0 to 4, I would like to have the output to be equal to 0. And if the BCD input from 5 to 9, I would like to have the output is equal to 1 if the input is 5 to 9. Now, notice that the output is X here, means don't care. If the input is from 10 to 15, which means that it is not BCD. Okay, it's not, we are not really supposed to receive this input from 10 to 15. So this is why we say that the output is a don't care. So I can draw the truth table, okay, for this function. Notice that from 0 to 4, the output is 0. So these are the zeros of the function. From 5 to 9, the output is 1. So these are the 1 entries in the function. And from 10 to 15, the output is a don't care because the output is not defined for a non-BCD input. It's defined only for BCD. So the don't care here can be either 0, it can be either 1. Okay, you can choose it, okay, any way that you want to minimize this function. Is this clear? That's the meaning of the don't care. So here we can show don't cares in the truth table, okay, for some entries when the output is not defined. Ali, you have a question?
Oh, yes, I didn't get what BCD means.
Did you listen to my first lecture at the beginning of the semester when I talked about BCD codes?
Oh, binary coded.
Decimal,
Something
yes,
like
binary coded decimal. We use 4 bits to code the decimal digits from 0 to 9. That's BCD.
Okay, okay.
All right. So don't forget about these things. We are not really done with the course. You should not forget. By the way, when I cover many of these concepts in this course, even when you finish the course and you go to another course, you should not really forget about these topics. Some of them actually are really important even in other courses. So we should not really forget about these topics. Right. So now the question is, how do I express this in sigma notation? Now we use the sigma to express the minterms. So here in this case, we have these 5 minterms. Now this is from 5 to 9. So I'm going to write 5, 6, 7, 8, 9. Notice that we are writing here a lowercase m to indicate that these are the minterms, and we are writing them in sigma notation. But it's also important to indicate what are the don't care. So I'm going to write sigma d. This is the notation, okay, which is used to indicate that these entries here from 10 to 15, their outputs is a don't care. So that's the meaning here of the D. It's a don't care. And you can see that from 10 to 15, the output is a don't care. So we write it in sigma D notation to indicate that this is the don't care. So remember this notation. It's very important because I really need to distinguish, okay, between the minterms, the don't cares, and the max term. So now we have 3 possible things. Either the output is 0, this will be a max term, or the output is 1, it will be a minterm, or it is a don't care. Don't care, it means that either way is fine. Okay, so we write it as sigma D to indicate that this is don't care. Now, what we need to do is that let us take this function that we have seen in the previous slide, and let us use the Carnot map to minimize this function to obtain a minimal sum of product expression for this function. So I'm going to draw the Carnot map. Now notice that I'm showing the zeros, I'm showing the ones, and I'm going to show also the don't cares inside the Carnot map. So this is 5. This is 5. This is 6. This is 7. The output is 1. These are the minterms. This is 8. This is 9. So these are the ones of the function. This is 10. This is 11. This is 12, 13, 14, and 15. So these are don't cares. From 10 to 15, it is a don't care. We have a choice, so we have to show the don't cares inside the Carnot map when I would like to minimize this function. It's very important to show the don't cares. Right. So in order to minimize, I have to find the prime implicants and the essential prime implicants. And of course, it becomes essential if it covers a min-term, which is not really covered by any other prime implicant. That's what makes it essential. Now, the nice thing about the don't cares is that you can combine them with min-terms because you can make the don't cares to be ones. If you make the don't cares to be all zeros, you might not really obtain a minimal sum of product expression. If you make all of them as ones, again, you might not obtain the minimal expression. So sometimes some of them will be ones, some of them will be zeros, so you might actually cover some of them while the others are not really covered. Right, so if we treat all the don't cares as zeros, okay, we make them zero entries, then these are my prime implicants and these are essential. So we get this long expression that has 9 literals if we make them as zeros. If we make them, treat them as ones, all of them as ones, we can do much better, okay, because we can combine the don't cares with the min-terms and we can simplify the expression to only 5 literals. So in this example, it is better to treat the don't cares as ones. So it all depends on the function. Sometimes we might combine all of them, sometimes we might combine some of them. Okay, Ahmed?
Yeah, I was going to ask about that. Do we change all of them at once or some?
No, you can actually decide that which ones should be covered and which ones should not be covered. In this example, it turns out that, okay, you can actually combine all of them. That will be even better because you can combine 8, 9 with 10, 11, 12, 13, 14, 15, and therefore you can simplify it to just one literal, which is 8. So combining 8 squares will be good. And we have covered all the don't cares in this example. So we treated them as ones, all the don't cares as ones. But sometimes in some functions, you might actually have say don't care somewhere, which is not being covered. That's fine. You don't really have to cover all of them. So if you combine the don't care with 1, it becomes a 1. If you don't combine it, then it remains 0. So you see that here we can select the values of the don't cares. We can select them to be either 0 or 1 to produce the minimal expression. Remember one thing, if you combine the don't care with the 1, the don't care becomes a 1. If you do not combine the don't care with the 1, it remains 0. Okay, so you can make it 0, you can make it 1, depending on whether you combine it or not with an min-term. So now we have a simplification procedure with don't cares. So the first step is to find all the essential prime implicants, like we did before, but here we cover the maximum number. Maximum number, again, maximum is very important, power of 2 of ones and don't cares. And you can combine the ones with the don't cares if they are adjacent. You can do that, but to make it essential, you have to mark the ones that make the prime implicant essential. It has to be a 1 because the target is to cover the ones, not the don't cares. But you can combine the ones with don't cares if they are adjacent to minimize or to maximize the block size, okay, the number of combined squares. Okay, and by maximizing the size of the block, you are minimizing the term. Okay, so that's step number 1, is to find all the essential prime implicant. And what makes it essential is that it has to cover a 1, a min-term, which is not covered by any other prime implicant. Step number 2, if you have covered all the ones with the essential prime implicants, you are done with step number 1. But sometimes you need step number 2 if you still have some min-terms which are not really covered by the essential prime implicants. You have to add prime implicants to cover the function. So you have to choose, like we did in the case before, so we choose a minimal subset of prime implicants that cover the remaining ones. And make sure to cover all the ones which are not covered by the essential prime implicants. That's very important. And minimize the overlap between the additional prime implicants. Now, you do not need to cover all the don't cares. This is very important. Some don't cares, you don't really have to cover don't cares. And if you have a block of don't cares, you don't really need it. Why do you need it? Okay, you don't really have to cover all the don't cares. So you can actually keep them uncovered, and these don't cares will be zeros. Now, sometimes a function can also have multiple simplified expressions like we have done before. So this is my simplification procedure with don't cares. Okay. Again, you need to practice this. I have an example about this. So you can see that we have 5 minterms, we have 3 don't care. So the first step for this function g is to draw the Carnot map. So you need to locate where are the places of the ones, where are the places of the don't cares. So this is the index here. This is 1, this is 3, okay, this is 7, 11 is down here, and 15 is here. Okay, so these are my minterms, the ones, the 1 entries. The don't cares we have at index 0, we have at index 2, and we have at index 5. Okay, so these are the don't cares. Okay, is this clear? Or this is 1. My handwriting is difficult. Right. Now, what are we going to do? We are going to look for the essential prime implicants. Can you tell me what are the essential prime implicants? So which squares should be combined?
With, without the
You
don't
can,
cares.
you may combine it with don't cares. This is fine.
From 0 to 2.
So from 0 to 2, you mean 0, 1, 3, 2.
Yes.
But is this essential? Let us look at the essential first. Essential prime implicants.
From
3, 7, 15.
15, 4.
We have 3, 7, 15, 11.
11, sorry.
Yeah. So basically we have the 11 and the 15 make it essential. Okay, so we can look at these two. Okay, so we can cover actually 0, 1, 3, 2, like you said, but this is not essential. The essential one will be 3, 7, 15, 11, which is the red block. This is one solution. We can write the expression. This is solution number 1. But notice that 0, 1, 3, 2, it covers this minterm here. And this one. The other ones are don't cares. You can actually get a different solution. So this is why I said that 0, 1, 3, 2 is not, and it is a prime implicant. It is prime, but it's not essential. What is essential is the red block. So you can see that now we have a different green block that will cover 1, 3, 5, 7. So we get a different solution. So we get a second solution. Okay. So the second solution, notice that CD is essential in both solutions, but the first one contains A prime, B prime. The second one contains A prime, D. Now, let me ask you this question. Are these two solutions equivalent? Yes or no?
Yes, doctor.
They are.
Yes.
Right.
They are equivalent.
In solution number 1, what was minterm? What was actually here the box, which is 5? Did we cover actually here the minterm 5? Did we cover this 5 at index 5? The X at this 5 here. Was it covered?
No.
So it is what? If it is not covered, then it becomes what?
0.
Yes. If it's not covered, it is 0. Whereas this is 1 and this is 1. In the second solution, in the second Carnot map, is this covered? Are these two covered? These don't cares. Don't care 0 and don't care 2. Are these covered? These were not covered, right?
No, yeah.
There was no need for them. So we made them zeros in the second solution, and we make this don't care. Now this is don't care 5. We make it 5. We make it 1. So therefore, we have different selections for these don't cares. So don't care 0 in the first solution, in the solution number 1, we made the don't care 0 and the don't care 2, we made them ones. We made them midterms. We combined them with the midterms, and the don't care at index 5, we did not cover it. So we made it 0. Whereas in the second solution, we did the opposite. We did not cover, okay, the don't cares at index 0 and 2, so we made them zeros. Whereas we covered, we combined the don't care at index 5, so we made it 1. So these are not equivalent expressions. So basically, you can actually prove that these are not the same, because the choice of the don't cares is different. Okay, we change the choice of the don't cares. So even though they are acceptable for the function g, but these are not really identical expressions. So using the properties of Boolean algebra, you cannot really prove. In fact, you can prove that they are not equivalent, because A prime, B prime is not the same as A prime and D. CD is actually the same CD, but A prime, B prime, and A prime D are two different terms. So one is not equivalent to the other. In the previous example that we have seen in previous slide, when you obtained 4 solutions, we did not really have don't cares. All of these 4 solutions are identical. They are equivalent for the same function. So they cover exactly the same midterm. But here, we change the values of these don't cares. Do you understand this point? This is very important. So even though we have 2 solutions, the selection, okay, of making some don't care zeros and other ones as ones, we change that, okay, from one expression to the next one, okay? So the only essential prime implicant is CD, while the other ones are not essential. So A prime, B prime, and A prime D are 2 different blocks, 2 different terms. They cover different don't cares, and therefore some of them will be ones and some of them will be zeros. This is my example about don't cares. Do you have any question about this? We can also have a minimal product of sums. I need to finish this topic. I only have 2 minutes left. Okay, let us take a look at this function again. We are going to obtain G prime. Now, when you obtain G prime, you complement the min terms. Okay, you get the max term. So you basically complement. But the don't cares will remain the same don't cares. So look at the list of. So look at here at the. So when you obtain G prime, basically you are complementing the zeros. They become ones of G prime. So we are complementing the max terms of G. They become the min terms of G prime. So you can draw it like this. This is now the K map for G prime. Okay. Now, what we need to do is that we need to obtain, remember that the don't cares remain don't cares in G and G prime. They are still the same don't cares, but the zeros of G, they become the ones of G prime. So this is why here I'm listing those indices that do not appear in G. They are not min terms, they are not any don't cares. So these now, they were the max terms of G, so now they become the min terms of G prime. So now we have the Carnot map, and now we can minimize. Okay, so we can obtain here a minimal, okay, expression for G prime, but that will be a sum of products. And then when we take De Morgan's theorem, so when we complement G prime, we get G. We use De Morgan's theorem, so we obtain here 3 literals for the product of sums. So what we have seen in the previous slide, we obtained 2 solutions, solution 1 and solution 2. Here we have a unique solution. Now notice that this don't care has not been covered. That's fine. You don't really have to cover it. So the minimal sum of product expression for G had 4 literals, but the product of sums has only 3 literals.